Welcome, everyone. I think we're going to go ahead and get started. My name's Linda Larson. I'm with the Smart Energy Design Assistance Center, and we are here to talk about building energy fundamentals as part of our Building Energy Education for Architects series. Just a few items of business while you're coming in. We're delighted to see so many people here. Please, if you have questions throughout the presentation, feel free to drop them in the Q&A box instead of the chat. We'll be more likely to see them there. We'll try to answer questions as we go, but we'll also have time at the end of the presentation for any questions that you would like to ask. We will be holding a few polls as well throughout the presentation, so be ready for those. Just simple questions about energy efficiency in buildings. And that's all the business items I have. We will be, can you advance the screen, Sean? Just wanted to take some time to introduce our sponsors here, our hosts. So Stacy Fingston, I hope I'm saying your name right, the Executive Vice President of AIA Illinois. Would you like to introduce yourself?
I sure would. Thank you, Linda. Hi, everyone. Stacy Fingston, Executive Vice President of AIA Illinois. Hope everyone's having a great week. We are so excited to have so many of you on this training today. We had over 250 architects registered, so that's just really fantastic. Also, I'd like to thank Linda and the great Hvac team for all of their work in creating this series. We hope you take advantage of the next two that are up on April 21st and May 17th. This was a priority for AIA Illinois in our budget this year to continue to work with Hvac in creating another wonderful series of energy efficiency trainings. I'd like to thank Brian Imus of Illinois Green Alliance and our co-sponsor of this event series, and also a valued partner of AIA Illinois. AIA Illinois and Illinois Green Alliance have entered into a partnership this year to do more work in creating educational opportunities around energy efficiency and also high performance work through events, webinars, and public outreach. And now I'll hand it over to Brian.
Thank you, Stacy. Again, my name is Brian Imus. I'm the Executive Director with the Illinois Green Alliance. For those that may not be familiar, we're a membership-driven organization of primarily AEC professionals who are passionate and committed to sustainability in the built environment. And we have recently engaged in a bold vision to get to a place where every single building in Illinois is net zero, new construction and existing. Key to making that happen are education events and programs for professionals, just like this one being hosted by Hvac. So thank you to Hvac for pulling this together and convening so many architects to learn about energy efficiency in buildings. Moving forward, I'd encourage folks to who are interested in learning more about our work and our partnership with AIA Illinois and others. We really want to lift up and bring greater attention to the high performance building successes that are taking place in Illinois, both for other professionals, but also just as critical, policymakers. It's important that they understand that we need to scale the type of work that you all do and use policy to remove barriers to make it possible to do so. And a great way to educate policymakers is to show them the great successes in energy efficiency and high performance building. And with that, I will turn it back to Hvac.
Thank you, Brian, and thank you, Stacy. It's a pleasure to be here with you, and we're grateful for both of you hosting our presentation today. So today we are going to today we have two presenters. Sean Maurer is our lead presenter and one of our senior building energy engineers. Sean, would you like to introduce yourself?
Sure. My name is Sean Maurer. I have a mechanical engineering background from the University of Illinois. I got my master's of mechanical engineering there. Have about going on 10 years of experience in the energy efficiency field now. Started out with Siemens Building Technologies and their building automation division doing energy assessments. Moved into residential sector doing home pressure testing and work like that. And then now I've been working with Hvac for almost 6 going on 7 years now.
Thank you, Sean. And my name is Linda Larson. I am the Education and Communications Director at Hvac. I'm happy to be here talking about energy efficiency with you today. So did want to let you know that we are an approved preferred education provider with the International Code Council. So if there are any code officials, building code officials here with us, you will be able to receive a certificate for that. We also have, this is also approved for continuing education credits from AIA. So what will happen if you would like to receive continuing education credits for this webinar, we will send you a certificate, and then after you receive that certificate, you'll get an email with a form that you'll fill out with your membership number, and then we will submit that to AIA and you'll be able to get credit. So a little bit about Hvac. Hvac is an applied research program at the University of Illinois. We've been in business for about 15, 16 years, and our mission is to reduce the energy footprint of Illinois and beyond. So as Stacy was explaining, this is the first of a 3-part series, our Building Energy Education for Architects series. Today, we're going to be focusing on fundamentals, and next month, we'll be learning a little bit more about renewables and zero code. And in May, we'll focus on passive house. So we hope you'll join us for all 3 parts of this series. And we're excited to continue this education journey with you. So a little bit about some of Hvac's other programs. We run a Building Energy Education Fundamentals program. This is funded by the Department of Energy with the audience of community college students. So if you're looking for, if you do any training, if you have new staff, you would like to help them understand some building energy basics, I would recommend that you check this website out. So if you go to smartenergy.illinois.edu, that's our website, and then B Fundamentals, you can see some of the different courses that we offer through this. We have some envelope basics, some mechanical basics, and some advanced modules. And some of what we're going to be covering today is an overview of what we cover here in our B Fundamentals course for community college students. We also, as part of our energy code training program, we offer technical support. So Sean and our other engineers answer questions almost on a daily basis about architecture and building code issues. So if you have a question, a technical question about something that you're designing, feel free to reach out. And then we have lots of online resources that are available, some tech notes, some energy smart tips. We'll show you a few of those in a minute, but all of this can be found on smartenergy.illinois.edu, our website. Also want to say that we deliver a fair amount of energy code training webinars throughout the year as well. So if you want to get on our list, you can sign up for our newsletter on our website as well. So here's just a few of our energy code program websites. So we are the energy code training provider for the state of Illinois. We offer workshops, webinars, online courses, and as we talked about, some technical support. We also have a bunch of resources. So if you need a crash course on what the energy code is, we have lots of tools and resources for that. And then here's just a few of our smart tips. If you go to our website and click on resources, you'll see many different kinds of resources. We have resources for specific facility types. We have some tech notes. We have some basics. So anything that you're wondering about with building energy efficiency, it's likely that we have written something about it. All right, so on to today's presentation. This will hopefully be a review for most of you. We're going to cover some of the most important things that matter when it comes to designing for energy efficiency. So our learning objectives today are to understand the importance of the envelope in long-term energy efficiency, identify some solutions to common envelope inefficiencies. We'll be covering a little bit of passive design principles, and then identify efficient HVAC lighting and plug load systems. So why design for efficiency? I think it's always good to start with the big picture here. Buildings in the US consume about 40% of our total primary energy. You can see here in this graph, we've got residential, commercial, and then industrial, which is also buildings in large part, but they also emit 34% of the total US greenhouse gases. So this is a huge sector when we're thinking about our impact on the climate. How can we make buildings more efficient? So many of our buildings that are designed today or that were designed in decades past, they're inefficient. They waste billions of dollars in energy costs, and they are contributing to our climate crisis. So we have this tremendous opportunity to design for efficiency. And there's a lot of reasons why we like targeting the architects, because you're the ones who can make buildings efficient from the start. It's easier and less expensive to make a building efficient from the start rather than trying to make it more efficient later. The upfront design and construction decisions that you are making as architects, they largely determine a building's efficiency. We can fix things later, but it's much harder and more expensive. The less energy a building uses, the less need to offset with renewables. So when we're thinking about that goal of net zero, CDAC, our main policy towards net zero is always start with trying to reduce the energy use as much as possible through energy conservation and energy efficiency. And then on top of that, you can load with renewables. So since we are the energy code training providers, we like to put in a little plug for the energy code in all of the presentations we do. This graph here shows the improvements, the efficiency improvements of the IECC, or the International Energy Conservation Code. You can see a big drop between 2006 and 2018. We're getting more stringent. The codes are getting more stringent. They're getting more efficient. Today's energy efficiency standards are over 30% more. They bring over 30% more energy savings compared to the codes of a decade ago. And they're continuing to drop, although a little bit more gradually. Some of the easier, more cost-effective measures to reduce energy have already been done, and it's going to get a little bit harder from here on out. But this is where we want to be. We want to be along this path to net zero. Certainly, we can continue to make efficiency improvements, but some of this is going to have to happen through offsets, through renewables. And we also like to emphasize that designing for efficiency is cost effective, especially if you consider life cycle costs rather than initial costs. So energy efficiency upgrades, they are going to bring a modest increase in initial construction costs. Not always. Sometimes it's, in fact, cheaper to build for efficiency, but you will see you'll see some costs for making the changes that we recommend today. But they will bring energy bill savings and reduced maintenance costs over the lifetime of the building. So you know, there's an estimate, there's a trade-off here. You might, for every $1,000 you add in first costs for making a building more energy efficient, you might see about a $5 monthly savings. So it's really a trade-off between increasing your mortgage a little bit, and then utility costs. So explaining it to the customer that way can be a good way to think about why this can be cost effective. And just want to put out there also that cost effectiveness is a big part of that energy code. When the Pacific Northwest National Laboratory does their models for cost effectiveness of all of the changes in the energy code, they make sure that it is cost effective, that the recommendations that they're making, the new requirements are going to be net positive when considering cost. So you're all architects, and what we like to emphasize is that energy efficiency can and should be included in all steps of the design process. We're going to start today with a little bit of orientation, massing, and layout. So just where are you going to put your building? What's the shape of the building? And then moving on to envelope and fenestration. After that, considering heating and cooling loads and lighting loads. And as you go through the design process, each aspect impacts the others. The choices that you make when you're designing the building envelope are going to impact the heating and cooling. So it's important to consider efficiency throughout the process, and then to consider how the choices you make are impacting the other choices down the road. So there are several building systems to consider when you're thinking about energy efficiency. There's the energized system, there's your HVAC, your lighting, your plug load. There's the non-energized system, the envelope, the fenestration, where your building is sited. Then there's the human system, and the human system is really important to consider because occupants are going to impact the energy use of the building. So this is the occupants going about during their days. We worry about controls. We want to eliminate human error from leaving the lights on, for instance. So considering this human system in your energy efficiency of your building is really important. And then underlying all of this is the climate and the surroundings. So have to consider the climate when you're thinking about energy efficiency. The decisions you're going to make here in Illinois are going to be very different than the decisions you're going to make in Nevada, for instance. Next slide. Okay, I think we have our first poll question here. All right, just take a few seconds to answer this question.
When is the proper time to start optimizing for design efficiency? As early as possible, after you get the primary HVAC systems chosen, after the primary envelope layout is completed, or after the client has specified most of their project requirements. We'll give that a few minutes. If there's any questions on what we've covered so far, again, please enter them into the question answer pane and we'll address those. We'll have a couple of stops for polls where we can answer questions throughout the presentation as we go along. We did have a question if a PDF of the presentation will be provided in the chat. Yes, I believe we are providing this. I believe the links that we have in this presentation, there are some helpful websites as we move along for references that will also be active. So when you receive that PDF, you should be able to follow links out to the references.
And I believe the webinar is also being recorded, and we'll share that recording with you. Okay, let's end that poll. Yes, so certainly the best time to start optimizing for energy efficiency is as early as possible. Got a few responses after the client has specified most of the project requirements. That's also a good place to start. But yes, we like to emphasize that efficiency should be considered from the very beginning. Okay. So siting, orienting, and massing, all of that will impact energy use. where you place your building, how it's oriented, and then the general shape of the building. And this placement, this orienting, can have a tremendous impact on the energy use, on the operation and maintenance costs. If you think about the impact of the sun on your building envelope, for better or for worse, you can see how that can happen. Next slide. So here's just a small diagram of how orientation affects energy use and energy performance. So we want to consider the solar orientation, both in the summertime and in the wintertime. We want to consider how breezes blow. We want to consider the availability of natural light so that we can perhaps offset some of our lighting energy use. And then we can also consider things like shading from vegetation, topography, or adjacent structures. So in general, what you're going to look for, if you're thinking of easy winds, you want to minimize east and west exposure for solar heat gain and winter wind protection, and then shade from summer sun, especially in our climate. And then there's a lot that designers can do to orient for natural light. So choosing an orientation and window placement that minimizes lighting use or maximizes daylighting can be a good way to think about energy, reducing energy use. So an east-west building axis would maximize the south-facing area. So bringing in some good light in the wintertime. Central atriums can daylight a building, the building core. So those are some things that you can do to orient for natural light. It's also important, though, to consider the trade-off. If you're orienting for natural light, you also may bring in some of that solar heat gain. So what's the trade-off there? Which one would you like to do? Which one is considering aesthetics and comfort and all of those issues, which one would you like to prioritize? So in thinking about building mass, we like to explain it in terms of, is your building envelope oriented or is it core, envelope dominated or core dominated? So envelope dominated buildings, that's where, they're typically smaller buildings. They have a larger surface area to volume ratio, and they require heating and cooling depending on the weather. So they're going to be envelope dominated buildings are going to be most impacted by the climate. Core dominated buildings, those buildings are larger. Typically, you'll have a small surface area to volume ratio, and they often require cooling year-round. So perimeter zone, the envelope dominated buildings influenced by climate. Core zone, they're going to be more influenced by your systems, your equipment, your lights. So the strategies you're going to use are going to differ quite a bit depending on whether you're envelope dominated or core dominated. Envelope dominated buildings are going to focus on that insulation, continuous insulation, no thermal breaks. Sean's going to cover a little bit of that and some problem areas in that in just a bit. And then focus on the windows. Core or internal load dominated, your larger buildings that have a larger core, you're going to focus on, you're still going to want to focus on the envelope, but it's going to be less important for consistent comfort, less important for your heating and cooling systems. And you might consider a little bit of daylighting and natural ventilation for offsetting loads for core dominated buildings. So building compactness is going to impact energy use as well. You can see in this little graph how these three building types are different in how much energy use they consume. You can see here on the top, you can see a bit of a difference in the heating load here. So the heating load is greatest for this building down here, and least for this building, which is more compact. And you can see also that it impacts the cooling load slightly as well, whereas the lighting and equipment stay relatively the same. So you likely use building modeling to design the buildings. You can do simple parametric runs to identify opportunities to optimize for energy efficiency, changing the layouts, changing the thermal mass, changing the orientation, and then seeing which is the most energy efficient option. Even if passive design isn't the focus, optimizing can reduce energy and improve resiliency. I'm going to turn it over to Sean.
Okay, before we dig into some of these envelope details, we do have one more poll question here. What impact does building compactness have on its energy consumption? Is it going to increase envelope and solar load impacts, have a negligible impact on building loads, or reduce envelope and solar load impacts? Just a quick note on this slide here. What we're looking at is mainly a big difference in surface area to volume ratio on these buildings. So the top chart, you've got a relatively large surface area of the building because you've got 5 individual cubes set closely together. The bottom one, you've got a little bit more surface area because of that tall tower. You've also got some temperature impacts from having a taller building. The higher up in the air you get, the cooler it is. So you have some impact on the heating loads there. And also, we'll see a bit later, balconies and thermal bridges have a greater impact on skyscraper facilities as well. But that middle building is the most optimal. It's compact. They've got a couple of buildings set close together there, where they've minimized the total envelope but maximized the square footage of floor area. So we'll go ahead and share those poll results here. Looks like most people have caught on to that if you're going to make your building as compact as possible, it's going to reduce those envelope and solar load impacts on your facility and make planning for building loads a little bit more predictable and easier to do. Okay, so now we'll move into the building envelope. Considering first that our presentations overall for this series are focused on kind of moving towards net zero, we really wanted to focus on the envelope because it has long-lasting impacts on the building. The envelope's going to last throughout the entire life of the building. So the choices you make for that structure are going to have a lot more long-lasting impact than the HVAC systems and lightings, where every decade or two you get new higher efficiency equipment that can be swapped in and improve building efficiency. The envelope, once you build it, you're kind of stuck with it. It's very expensive to go back and renovate an envelope to add insulation and difficult to do properly. And so focusing on that first with your initial designs, paying attention to your building siding orientation and massing, trying to take advantage of even just slight benefits in passive design there, even if it's not a primary focus, taking advantage of that as much as possible improves the resiliency of your building. And then when you focus on the envelope as far as insulation, fenestration improvements, you're decreasing the costs you're going to have later on for sizing of your HVAC systems, ventilation systems. And so there's a cost trade-off here that happens with the envelope, where some of that initial focus, even though there might be some additional cost up front for the envelope design, you can save on those costs on the HVAC and lighting design. And this is just an overview of the impact the envelope has on systems. This isn't a direct envelope energy comparison, but just how much of the building's total energy consumption does the envelope impact overall. And so like in commercial buildings here, heating systems, cooling systems, lighting and ventilation are all impacted by the envelope. So that's about 54% of the building's loads. Varies back and forth a little bit depending on your climate zone and your building design. But essentially every component of the building that isn't plug loads, lighting, or other miscellaneous loads in the building like appliances is impacted by the envelope of the building. And so having that primary focus there early in design is going to do the most for reducing overall energy consumption. As I noted earlier, the envelope components are going to outlast mechanical systems and lighting systems. You know, your envelope life for a building is generally designed for a 50 or more year lifespan. We've got buildings that are hundreds of years old and still in use. So the envelope is a permanent part of that structure. Paying attention to its design early on is going to have that long lasting impact. Where when you're looking at HVAC systems, lighting, you're in a 15 to 20 year lifespan. For lighting, it's more like an 8 to 10 year lifespan. And something else to consider is if you have a power failure in the building. If you've got a poor envelope, you're going to change to closer to the outdoor conditions much more quickly than if you have a well-designed, well-insulated envelope. And so in terms of resiliency for the building, if you design for that little bit additional insulation, a little bit better windows, a little bit better shading to prevent solar loads, you improve the ability of that building to maintain comfort conditions even if the power goes out. And then proper design of that envelope contributes to the long-term comfort of the occupants. You don't have people sitting next to windows feeling drafts and complaining it's cold all the time. You don't have variations from space to space in temperature based on solar loads or uneven distribution of heating and cooling. And then proper design of daylighting is going to provide, excuse me, lighting into the space without introducing glare. It's going to minimize that lighting use of artificial lighting. There's health benefits to using day lighting that have been noted in research. So again, focusing on this early design is going to have a lot more impact even outside of energy as far as the health and comfort of the occupants in the building. So there's a lot of non-energy benefits here. High performance envelopes, you're going to have improved air and moisture control, improved durability of the envelope, making sure that we're keeping rainwater out. We're allowing structures to properly dry should moisture actually get into them. Expansion and contraction is minimized as much as possible, so we're not pulling apart building joints that are preventing air leakage. Things like that are much better when you've got a high performance building envelope design. You have better maintenance of indoor air quality because you don't have leakage coming through the envelope carrying pollen, or if you're in the city, you've got vehicle fumes, things like that. You have a more consistent indoor environment when you've properly accounted for daylighting and the solar gains attributed to that with shading devices. And you've properly accounted for thermal bridging in the building. That's going to provide a more consistent indoor temperature where you're not going to have swings due to the thermal bridging or windows or solar gains. And again, the increased resiliency of that envelope, if you go with a high performance, you get even more benefit out of that resiliency, where buildings can maintain their comfort should the power go out. So the things that we think have the most impact on the design, the things that really matter, one of the key things is focusing on that continuous insulation. You know, if you look at the baseline energy codes, particularly in residential buildings, there are ways to design homes that don't have that continuous insulation. It's the R20 wall design. But that does have that trade-off in that you have more thermal bridging in that envelope, which does raise risks for condensation in that assembly due to those thermal bridges, and a little bit of discomfort, particularly where you've got a lot of wood mass like window headers or areas where there isn't thick insulation. So using proper detailing to avoid those thermal breaks, improve the insulation, make sure it's continuous. It's going to make sure you get the best performance out of your insulation layers. Next, after that, and kind of integral to insulation, is making sure your buildings are airtight. If you've got air leaks in the building, that brings in humidity, outdoor pollutants, drafts into the building, particularly a concern in the wintertime where people feel those cold drafts more so than they feel hot drafts. So making sure that all the the building joints are sealed properly, that you've got that continuous air barrier is very important for maintaining the efficiency of buildings. And then the other control layers are also important just to maintain the integrity of the building. If you've got a break in your water control layers or your vapor layers, now you've got the ability to create condensation or moisture damage within your assemblies, and that can lead to health impacts for the occupants inside the building and degradation of the structure itself. And finally, proper fenestration selection. You want the low solar heat gain coefficients. You want lower U factors so that you've got improved insulation from those window assemblies. Really trying to enforce here that you want to exceed code. Code is kind of that bare minimum compliance requirement. It's like getting a D on a test. You just passed. So if you can go beyond the code in any ways and then trade off somewhere else as far as sizing of your HVAC equipment or the amount of lighting you need to install in a space, then we highly recommend that you focus on those areas to improve the envelope first. We've touched on this quite a bit with our energy code presentations and some of our other webinars and workshops, but paying really close attention to your control layers and coordinating those, not only just in the planning process, but also in installation and working with subcontractors and builders on site and making sure that the different trades are aligned so that, say someone's put up a good wall assembly, but then HVAC or plumbing comes along, they've got to cut holes in it to run their utilities into the building, but don't properly seal it back up. Making sure that people know their responsibilities for ensuring that these control layers are maintained throughout the structure is very important. The common example we see a lot here is the roof wall interface at parapet walls. Coordinating between the roofing contractors and the framers that are putting up the wall is sometimes difficult, and making sure that those control layers are coordinated between those two groups. So having a plan for that in your design phase and also through the construction phases of the building. Excuse me, I've got a sore throat, so I apologize for coughing through the presentation. But one of the big things here to focus on that will really help with the continuity of your control layers is also focusing on eliminating thermal bridges. If you're looking at the way your different assemblies come together, the wall to the roof, the wall to the foundation, corner joints, things like that, if you're paying attention to those and making sure that insulation is continuous there, then most likely you're also going to have continuity of the other control layers. But the big thing to be aware of here is that continuous insulation is going to avoid that thermal bridging and give you better performance out of the installed insulation. What we're showing on screen here are two wall assemblies. One is an R20 wall with wood stud framing, but no continuous insulation on the outside. If you take that same wall assembly, put R15 bats in that wall assembly with an R5 on the outside, it's a 6.25% improvement in the insulation value of that assembly. So thermal bridges can have a big impact on the building's energy consumption. And we can't stress enough to be aware of where those thermal bridges are at and looking into ways to minimize those bridges or eliminate them. Some common thermal bridges that we run across, masonry assemblies without continuous insulation. If you're doing a steel structure on the inside with insulation there, most codes don't allow that anymore. You've got to have continuous insulation with the masonry wall. But we've seen that in the past with older buildings. And so when you go to an existing building and are looking at upgrading that facility, if you're doing major overhauls to the envelope of that structure, you're removing brick and putting up a different panel or doing an IVE system or something like that. Again, focusing on those thermal bridges and making sure there's continuous insulation around that structure is important. Making sure there's that continuous insulation behind studs and structural members, as those are common thermal breaks. With steel framing in particular, when you're looking at the insulation value between steel's framing members, that rated insulation value gets cut by 60 to 70% just because of the high conductivity of metal framing members. Balconies and porch awnings are really common thermal bridge. You've got that concrete slab that comes all the way out to the outside. It acts like a radiating fin. Fenestration framing, paying attention to the way your windows are framed, having proper thermal breaks in that window framing, aligning it with the insulation layers of the building, all helps to make sure that there's a continuous insulation layer around windows. Assembly joints and corners, some examples on the screen here of just bringing together the corners of a building. There can be thermal breaks there and air breaks there if it's not properly detailed. Brick ledges on the foundations are another common area where there's, particularly if you're insulating on the inside of a foundation wall and then you've got exterior insulation for the above grade walls. There's a really big break there in that foundation that allows heat to transfer through. Something that we found is an excellent resource here. There's a Canadian company that's developed a lot of detailed common thermal bridging constructions in buildings. And so the images you're seeing on screen are from that catalog, but they have, along with just detailed drawings of what different assemblies are, they also rate them by their thermal transmissivity. So it's a good reference to go to and look at, kind of what are the optimal design strategies for different thermal bridges in buildings. But this is what I was talking about for taller buildings with balconies on them. If you're looking at that, it's a multifamily structure there. Looks a lot like that radiant floor heating there. You've got the fins on that coil that allow it to more quickly transmit heat into the surrounding environment. That's why we have fins on radiant systems, HVAC coils. But when you do that with a building, you're dramatically increasing the heating and cooling loads on that building if those balconies are not thermally broken from the inside of the building. So these are some examples from that thermal envelope California catalog again, just showing different ways of breaking that thermal bridge for slabs. So kind of the typical design there on the left where you just got the concrete slab going to outside. It's got a very poor conductivity rating. The one in the middle there is using a structural thermal break. I'm forgetting the name of it off the top of my head, but essentially you've got the rebar supporting the structure of that exterior slab, but you've got a piece of foam there that's providing some continuous insulation. Where now you've limited that conductivity to just the rebar members that are supporting that slab going through that insulation. And then kind of the best option on the far right there is instead of putting a concrete slab out there, do a metal frame structure where that metal framing is supported off the building by hangers, and you can put continuous insulation behind it. You get a drastically better improvement in the thermal performance of that structure. As far as what the cost trade-offs are for that, I'm not sure. We haven't really looked into that yet. But some considerations to make for your design options. And you can look at trading off the cost versus, since they give you conductivity, you can factor that into your building models as far as figuring out what your envelope loads are and see what that trade-off is and see if it makes sense to you. Another very common issue we see is with parapets on rooftops. And probably the best advice we've seen for those is to treat them kind of like vertical balconies. You've got this wall structure that's preventing wind uplift for the roof assembly, the membranes on top. But if you don't thermally break that from the building, that corner where the wall and the roof meet there is an incredibly conductive area where you get a lot of heat loss. We've also seen with some designs of these parapet walls that even if you wrap insulation up and over and you fully enclose that parapet with insulation, because it's exposed on 3 out of 6 sides to the outdoor environment, you can still get condensation in there that will then drip down into the wall assembly and can cause issues. So if you can just break that off from the building structure entirely with a thermal break, making sure your vapor barrier is also tied in there, you can eliminate that condensation risk that you have with kind of the more typical designs for parapet walls. So just one of the things to consider. There are other options available. Something that's coming with the 2021 version of the energy code for commercial buildings, and we've seen with residential buildings for a long time now, is verification of that air barrier through pressure testing. It can help catch issues like what we're seeing here, where you had the structural I-beam for the floor, with another I-beam on the outside of the building for the rain screen structure that just covered up a large hole in the building. This was about a 10 by 14 inch just opening in this structure. And in this particular instance, they had open returns for a heat pump system, and the heat pump system just couldn't keep up because it was drawing outdoor air straight through that opening instead of conditioning return air from within the building. And it wasn't sized for those loads. They had humidity problems, they had temperature and comfort issues. Once they found these openings and sealed them up, there were 6 patios in this particular building that had these openings. They corrected all those issues and saw a dramatic drop in their energy consumption. So when you're looking at building designs and stuff, figuring out where you have complicated corners in the building, usually the wall of the roof structure, corners of the building where things are coming together, making sure that you've got proper detailing in your drawings. It's going to explain to the installers how to properly air seal that, and make sure that that's going to have a continuous air barrier there to seal that up properly. Something to be aware of in the designs of your buildings is that some materials combine control layers together. So what we're looking at here is 1 inch or more of XPS is a class 2 vapor retarder, as long as the seams are sealed and taped properly. Similar to roof designs, you can improve that air sealing performance by overlapping 2 layers, so the seams aren't aligned with each other and have a direct pathway through that insulation. 2 inches of closed cell SPF is an air barrier and a vapor retarder, depending somewhat on the composition of the foam. Again, it has to be closed cell for 2 inches. You get an air barrier with open cell foam at 5 to 6 inches, but it is vapor permeable. And so paying attention to the materials you're using in the building, alignment of those materials in your structure to make sure that you've both got a good vapor and water control barrier, but you haven't set up a situation where you trap moisture within the wall assembly where it can't dry out easily. And so that's something to be aware of with some of these control layers and materials selection. The next thing is paying attention to the control layer choices and analysis throughout the installation process and design process. Initially, you can use computer models to check on, I've built this particular wall assembly. These are the materials I'm going to put in it. Is it going to have a potential risk of condensation or moisture damage? The Hvac program is a program that a lot of agencies use for that analysis in research, and it's starting to grow into passive house design. Passive house requires Hvac analysis of their assemblies. In your plan review, you want to make sure that you've got proper detailing that covers joints, transitions, and any other potential breaks in your control layers. Something we recommend for thermal and air barrier testing is a pencil test. Trace around the outside of your building your insulation layers. Anywhere you've got to make a sudden jump, pick your pencil up. That's probably where you've got a thermal bridge or a break in your air barrier. And then site inspections are also important. So what we're showing on screen here, before this material gets covered up by the exterior cladding, go through, have some commissioning agent, one of your contractors, somebody assigned to go and look at the air barrier continuity and make sure that if there are breaks in a self-adhered membrane or a fluid-applied membrane or other, whatever you're using for your control layers, that they're catching issues in those breaks, wrinkles. With spray applied systems, you can get bubbling in that allows air transfer and moisture transfer. With like Hvac type materials, making sure that you've got proper installation of the hangers for those, paying attention to how long those materials have been exposed to the elements, and planning that out, as a lot of these materials degrade when they're exposed to direct sunlight, high winds, things like that. So again, these are all important components of the design process that should be factored in to make sure that you're getting the most out of your envelope designs. For fenestration, again, selecting low solar heat gain coefficient glass, and low U factor glass. It's going to reduce how much heat is coming into the building and how much heat is lost out of the building. So one thing to consider though, is if you're looking at a building, even the best windows that we have on the market are about an R6 to an R7 overall insulation quality. Compared to most of our wall designs are somewhere between an R20, R18 kind of average for the insulation value. So even the best windows have a significantly less insulation value than an opaque wall assembly. So proper design to minimize how much glazing your buildings have while preserving views to the outdoors, daylighting coming into the building, will go a long way towards high performance design. When looking at window ratings, what we're showing here is the NFRC tag for a pre-assembled window. For site-built windows, there are component modeling programs, and there are also pre-assembled assemblies that are in a database from NFRC that give you these ratings for their windows. And again, you want the lowest U factor, the lowest solar heat gain coefficient that's effective for your project. The only exception really is if you've got south-facing glazing that you're trying to do passive solar gains with. You might want a slightly higher solar heat gain coefficient there for winter assistance in heating, but you want to have proper design of shading devices over those windows to make sure you're not getting that heating in the summertime when you don't want it. I think we've got another poll question here we'll launch. So why should designers focus on eliminating thermal bridges? To improve overall insulation effectiveness, reduce the risk of drafts, temperature variation, or reduce the risk of condensation of building assemblies, or all the above. And then our second question, why do high performance buildings focus on the envelope? The envelope lasts life of the building, the envelope works to mitigate indoor environmental changes, envelope focus can minimize HVAC capital and operating costs, or all the above. And we do have a question in the Q&A that's come in. How do you make sure contractors and trades are actually going to carry out such high quality construction? Any suggestions? It starts early on in the construction process with meeting with those trades and making sure they understand those responsibilities and their roles in the construction of the building. Also, proper detailing on your plans. We've seen a lot of plan drawings where you've got kind of the typical cut and paste kind of details for parapet walls or something like that, instead of a detailed updated design for improved efficiency on those building details. Or some details are just assumed that the trades will do them correctly and they're not properly detailed in the drawings for kind of common building joints and assemblies. And so in those situations, we recommend first on your plan drawings, making sure that you've got details for complex building joints and materials like that. In your specifications, making sure that it's properly detailing application procedures, things like exposure of building control layers to the elements before they're covered up by cladding, things like that. To make sure that the specifications also reflect the installer's best practices. And then regular meetings through the construction process will help as well. Just checking in with contractors. Is there something they've run across that they don't know how to properly detail or construct, or something in the drawings isn't lining up? Regular meetings to check in on those things. And then there's also third-party commissioning agents that can look at structures as well and help ensure that your plans are being followed. So there are a few different ways to do that, but it takes a lot of communication for sure. Let's go ahead and...
Sean, there was one other question that I took a pass at answering, but I thought you could address it as well here. Does the Illinois code require existing buildings and bringing them up to code with regards to a curtain wall system? For example, a 1970 building, single pane glass, no thermal breaks.
So for a lot of existing buildings, existing structures can get grandfathered in. There are certain exceptions to that. If you're, like for the particular instance of fenestration, if you're expanding fenestration beyond what it originally was, new fenestration must have updated solar heat gain coefficients and U factors to meet the code. If you're just replacing glazing, but not the entire fenestration assembly, you can go back with an equivalent to the original. If you're doing change of occupancy in a building that's going to result in an increase in energy consumption, then you do have to do a full envelope compliance as well there. So it kind of depends, but for the grand majority of projects, we see that for minor changes to the envelope, they can be grandfathered in. More significant upgrades do require full compliance. Okay, we'll end our poll and share the results here. Looks like everyone's caught on to both of these questions, that the answer is all the above for both of them. For thermal bridges, you're getting improved insulation effectiveness as you're not having that loss through the conductive members of the building. You're reducing the risk of drafts and temperature variation that result from those thermal bridges having a colder surface inside the structure. And you reduce the risk of condensation in building assemblies as well. So you're increasing the overall resiliency and durability of your structure. And then as far as high performance buildings and their focus on the envelope, again, it's going to last the life of the building. It's going to mitigate indoor environmental changes, particularly if power is lost. They can better maintain indoor comfort conditions for longer. And they also minimize that capital cost that you're going to spend on HVAC equipment because your loads are reduced to begin with. So good. Looks like everyone caught on to all of those. Excuse me a second. Okay, so now let's take a look at HVAC equipment optimization and where to focus on those particular systems. One of the things that can really help with the efficiency overall of HVAC systems is use of modular systems that can adapt to loads. Variable speed fans, variable speed chillers, modular chiller systems where you got a number of smaller units instead of a couple of really large units. Those can improve the overall operating efficiency of a chiller system. And they also have benefits for maintenance long-term in that they're easier to remove from the building without having to take out a wall of the structure or something like that to access larger equipment. Making use of heat recovery ventilation, particularly now post-pandemic when people are looking at improving indoor air quality through increased ventilation. Without heat recovery, that's going to be a significant increase in the cost of operating buildings. So looking at energy recovery wherever it's available is going to help minimize the loads on HVAC equipment and can help reduce the capacity required for those systems. Making use of system and building interactions, taking a look at, you've got a heat source in the building and you've got a heat demand somewhere else. Can you interconnect those where the heat load can supply the heat source? Or vice versa. Understanding human comfort factors and their impact on HVAC systems. We'll touch a bit on what kind of impacts human comfort the most when you're looking at temperature in a space. And then designing low energy HVAC systems that control outdoor airflow and maximize equipment efficiency. So for heating, cooling, and ventilation minimization, again, looking at modular systems, they can more easily adapt to loads. We see commonly with a lot of particularly larger buildings, you'll have single large pieces of equipment, like a couple of chillers or something like that. But as they reduce in speed, they also lose efficiency a little bit. There's an optimal range where they maintain peak efficiency just under peak loading. And then peak loading is usually a slight drop in efficiency. And so if you can look at installing multiple smaller pieces of equipment, you've got better redundancy to those items, and they're more likely to maintain their peak efficiency operation. Also looking at hybrid systems where you're mixing different types of chillers, where maybe a centrifugal type chiller is more efficient closer to peak loads, but another type of chiller system might be more efficient at reduced loads. Something else to be aware of with modular systems, particularly modular boilers and modular chillers, they have a small footprint that can easily fit through maintenance doorways. And so future maintenance and replacement is going to be reduced in cost. Heat recovery ventilation, depending on whether you're doing heat only or total energy recovery, can reduce heating and cooling loads by 50 to 85%. And again, if you're reducing those ventilation loads, you can also reduce the capacity of the equipment and save on the capital cost of that heating and cooling capacity. So you can put in smaller chillers and boilers to begin with, or smaller heat pump systems. When looking at building interactions, do you have a high heat source like an electrical room or an electrical closet that's producing a lot of heat? Then you've got a heat demand in the building like domestic hot water or kitchen water, something like that. Can you look at the potential to recover heat from those high heat spaces through a heat pump system and use that as a means to recover that energy that would otherwise be exhausted out of the building through an exhaust fan? Those can help improve the efficiency overall of those systems and design. Looking at compact designs as well, optimizing plumbing, duct, and electrical runs where you've got a core service corridor in a building that can then branch out in shorter runs, can reduce associated energy losses from having long runs across a building of plumbing and ducts, electrical runs, and also reduce the material cost for installing those things. Particularly in residential buildings, we're seeing a lot more compact designs where you've got a central utility closet with all your hot water sources as close to that closet as possible to reduce losses from hot water piping. Similar things can be done with skyscraper structures where you got a central shaft for elevators. You could do the same thing for ventilation, ductwork, and things like that. And then they branch out in shorter branches to floors in the building. The more compact your building is, the easier it is to do those kinds of designs. If you have a more sprawling design for your building, you're going to necessarily have longer runs of these systems and greater associated losses with them. Some design targets for high performance buildings, some things that we've looked into. The New Buildings Institute has 0 energy performance targets. These are part of the Zero Code when looking at the performance path. But they take essentially code minimum calculated energy use intensities and then take them a step lower so that it's much easier to install renewables and alternative energy systems than for a building that has typical energy consumption. So you can save on the capital costs for renewable projects. Passive House as well has significantly lower building energy use intensities because they do focus on passive design, doing as much as possible to get natural control of building systems instead of mechanical control, and then supplementing those as needed with mechanical systems. So touching on how humans feel comfort and control our body heat, something that's very important to know is that conduction and convection, the primary components that we feel from controlling air temperature in a space, are actually a fairly small percent of what makes us feel comfortable in that space, only about 18%. Another 20% is associated with airflow and evaporation of sweat off the skin. But primarily, most comfort in a space is determined by radiant losses or gains from the surrounding environment. So what we're showing on the screen here, the top left image is air cooling. So we're maintaining lower temperatures for that discharge air. We've got increased energy consumption to do so, to deliver that cooler air into the space. But the surfaces in that space are kind of a median temperature. And so particularly next to the windows there, you can see there a higher temperature. An occupant sitting there is going to feel much warmer than the person sitting closer to the camera there in the bottom right corner of that image. When we look at radiant cooling systems, the bottom right image there is, sorry, bottom left image is a radiant cooled chilled beam type ceiling system. Where now your air systems, when you're doing ventilation and things like that, can provide more moderately tempered air. So you're not having to cool down to 50, 55 degrees. You can provide neutral temperature air, neutral humidity air. So you minimize the costs for conditioning ventilation air. And since you're providing direct cooling in that space, you also reduce ventilation for recirculated air. So some benefits of radiant systems and paying attention to the radiant environment is that you can minimize your ventilation fan sizes and improve overall comfort and temperature consistency within those spaces. Unfortunately, for most building designs, we focus on fully mixed air conditioning. When most people think about making themselves comfortable in a space, they think about going over to the thermostat, turning it down so that the air temperature changes. Where radiant systems can definitely provide much more comfort at much less energy consumption than air conditioning systems. So this is also why it's important to focus on the envelope, going back to that initial design. Improved insulation of windows and walls, getting rid of thermal bridges is going to maintain that more consistent radiant temperature in the space that we feel more than other conditions in the space. And so you have better control overall of space comfort. You also have better control of space humidity, which again impacts your HVAC sizing. If you've got humidity coming into the building, getting pulled back into the return of the system, that's an additional latent load that system has to then manage. If you seal that up tight and you control that ventilation air through a dedicated ventilation system or your central air conditioning system, you've got much better control over that ventilation air. And you eliminate drafts that create uncomfortable conditions for the occupants. Again, particularly noting in the wintertime, people sitting next to windows or exterior walls can feel that convective draft off those cooler surfaces that leads to a lot of building comfort complaints. And then you're also going to be able to downsize the overall capacity of your HVAC systems and target them to deliver optimal air conditions for humidity and temperature. And you're also going to be allowed a broader range of comfort when you have kind of that balance between radiant temperatures in the space and air temperature. Something we like to touch on again, making sure that your equipment is properly sized to buildings, avoiding rule of thumb calculations. This is just a residential example where the typical rule of thumb is about 500, 600 square foot per ton. And we're finding now with even code minimum buildings that that's closer to 1,200 to 1,500 square foot per ton. And some high performance buildings are much better than that. Same thing with commercial buildings. If you're getting kind of a rule of thumb calculation, again, we kind of see that 500 square foot per ton applied to commercial buildings as well. You kind of know that they haven't done proper work for the sizing of that system. You might want to have them go back and do a proper sizing calculation or a building model, whatever method they're using to determine the equipment sizing. Controlling outdoor air. For demand control ventilation, typical standards in the past are about 1,100 parts per million. We see slightly higher set points now, about 800 parts per million to increase ventilation just due to the pandemic and people's concerns about indoor air quality. Really, if you can ensure that your buildings are actually meeting their ASHRAE 62.1 ventilation rates, or 62.2 for residential buildings, by and large, they're going to have good indoor air quality. The problem runs across where buildings are designed for those ventilation rates, but they don't actually achieve them. Poor duct runs and things on exhaust fans reduce their exhaust rates. Unbalanced air flows out of ventilation systems can reduce ventilation rates in spaces. So having a proper HVAC commissioning process in place to ensure that you've designed for these ventilation rates, you're actually achieving them, is also very important, not just for indoor air quality and maintaining the health and safety of occupants in your building, but also for the proper sizing of that equipment. Something else to consider is optimizing your DCV controls. There's different ways to do DCV control that are more beneficial for different space types than others. You can do CO2 control in spaces that have irregular occupancy patterns. Private offices, classrooms are kind of decent examples. Timed ventilation rates are kind of better for spaces that have regular occupancy patterns. Occupancy sensing type controls are better for spaces that have widely varying time of use, but relatively consistent occupancy numbers. And so what we're touch on here, multiple types of sensor options exist. CO2 is that most common implementation. A direct count of building occupants is going to be more accurate, but it's harder to implement in most buildings. We have seen for some like stadium type structures or auditorium type structures where they can have door counter sensors that count occupants going in and out of the building and adjust ventilation that way. But for CO2 control, typically you're going to see those in spaces that have variable time of use, but relatively consistent occupancy levels. So making sure that CO2 measurement is applicable to the space. CO2 for high and variable occupancy zones. Occupancy sensors can be used in private offices where you know it's just that one occupant. And so your ventilation can be tied directly to that occupant's presence. And time of use schedules are good for lobbies or zones with known schedules, relatively consistent occupancy rates. And this has a couple of benefits. One, you're going to get better performance out of your ventilation system. And two, you're going to mitigate the cost of having a bunch of sensors that aren't really as effective as they could be if you're trying to put CO2 sensors in every space. Or as we sometimes see, putting those CO2 sensors in a return duct or something like that, where it's averaging multiple spaces. And now those individual spaces don't necessarily get the ventilation they need when they need it. So that's optimizing that DCV system is going to help minimize those ventilation energy consumption. And then minimizing your building energy consumption through minimizing how much ventilation air you have to move through the building. Again, as we touched on with radiant systems, if you're providing radiant heat and radiant cooling in a space for that direct sensible control, then your ventilation air is limited to just what it needs to provide your ASHRAE ventilation rates. And comfort control is then provided by direct equipment in the space or a radiant system. Radiant panels, chilled beams can provide that comfort without forced airflow. You're limited just to the energy for pumping fluids through those radiant structures. If you're using conditioned airflow, minimize the need for ductwork. Using things like VRF systems where you've got primarily refrigerant piping, but the unit is just recirculating air in that space. It might have a dedicated outdoor air system ducted to it where it's also conditioning the outside air a little bit. But mini split heat pumps and VRF systems are an excellent way to minimize that airflow to just what you need for ventilation, and your space conditioning is provided by a much smaller fan within the space itself. Dedicated outdoor air systems are also a great way to minimize ventilation energy because they bring all your ventilation air, your exhaust air, to a common place where you can now put a heat exchanger on that and recover energy from your exhaust air and put it back into your ventilation air going into the building. It's also going to reduce that fan energy for ventilation, where if you've got mixed air coming to the unit as well as outdoor air for ventilation, the fan must be sized significantly larger to handle both those airflows. You reduce the overall size of the heating and cooling equipment, and you're decoupling temperature and humidity control for ventilation air. So you do humidity control through that dedicated outdoor air system. You temper that air to a mild neutral condition, somewhere around like 65 degrees and 55% relative humidity might be common. Send that to the space, and then you've got a heat pump in the space or a terminal unit there that's doing most of the recirculating for that dedicated space, and then conditioning that air in that space with cooling coils and heating coils. when paired with ductless systems, there is a recommendation to oversize or dedicated outdoor air systems a little bit so that you can provide economizing airflow. The recommendation is 40 to 60% of your dedicated outdoor air systems capacity at your design extreme weather conditions. And then when you're in mild conditions, you can get free outdoor air ventilation. You can throw that thing open, pump as much free cooling into the building as you want during economizing periods. It's actually a common practice for a lot of net zero buildings. And the other thing is when you're looking at your HVAC systems, if you're looking towards net zero, which is kind of the focus of this series, focus on electrification. Try to get away from combustion heating appliances and go with heat pump technologies that, now you can directly tie their operation to a solar field or a wind generation, and make use of that energy from a renewable source. Select high performance HVAC equipment. Heat pumps are much more efficient than gas or electric heating. So gas or COP is essentially what your annual fuel utilization efficiency is. And it can vary from 80% for steam systems up to 96% for condensing furnaces. If you're using straight electric strip heating, that's a COP of 1. It's 100% efficient. But when you go with a heat pump where you're moving that heat instead of generating it, now you can get much higher efficiencies, particularly with low temperature heat pumps that have come out with recent technology that can work down to negative 15 degrees outdoor temperature and still provide heating through the heat pump instead of switching to an electric resistance. You've got much greater efficiency there. There is a consideration that gas does have a lower unit cost, and so it's typically less expensive to operate, but it's a lot harder to offset that with renewables if you're targeting net zero. It's harder to find renewable sources of combustive gases. You would have to tie into renewable natural gas that's produced from wastewater facilities or something like that that's doing digestion. It's a lot easier for buildings to connect to on-site or off-site renewable solar and wind credits to reach that net zero goal. If gas is used, again, stressing high efficiency combustion systems, modular systems that can maintain operation at their peak efficiency for longer throughout the year is very important. So we have, I think, yes, we do have a poll right now. Oh, nope. I'm sorry. We want to cover the lighting section first. One of the questions is about lighting. So let me go through the lighting and plug loads first, and then we'll get to our last poll question. For lighting and plug loads, focusing on LED, high efficacy lighting, and proper lighting controls. Design your lighting for the need in the space. There are ways to optimize how much lighting you put into a space based on how it's used. And then for appliances and plug loads, focusing on Energy Star and high efficiency equipment is an excellent way to reduce those loads. So when looking at lighting and power, we've touched on daylighting already. It's going to help reduce lighting loads in the space during daylight hours when the sun is out and shining. Being careful to design those systems to diffuse lighting into the space. I've seen a lot of buildings where you've got floor to ceiling windows facing east or west or south. And at particular times of the year, you get direct sunlight through those that creates glare. And now people are closing blinds or shutters or other shading devices in the building, and you're not getting the benefit of the daylighting you designed for. Excuse me. You're not getting the benefit of the daylighting you designed for. People are still using artificial lighting when there's daylight available. So paying particular attention to glare reduction technologies, could be fritted glass, could be sheer curtains, light shelves. There's lots of ways to help get daylight bounced deeper into spaces and diffuse it where you're not getting that glare spot that's hard to see around. And then when you're selecting technologies for the building, focus on high efficacy LED lighting. New fixtures are typically designed specifically around LEDs, and so they're a little more efficient than retrofit fixtures. but they can reduce lighting power by 50%, and we've seen some that can reduce lighting up to about 70%. So there's a bit of a range there. But that high efficiency lighting is going to do a lot to reduce not only your lighting consumption loads, but all that light that's used in the space also ends up as heat in the building. And so the more you can reduce your lighting loads, the less cooling capacity you need for the structure. We've done a lot to improve lighting efficiency, as you can note here, but it still makes up a significant share of our electric use. And so that's where we start touching on controls and lighting design. So here we're looking at lighting for the need in a space, and comparing general lighting for an office type space versus dimming that general lighting a little bit and providing task lighting. You can see here about a 250 watt savings in the installed lighting for this space by providing task lighting that's dedicated to the use, and then general lighting that's a bit less than you would normally install when you're trying to cover both general lighting and usage of the space by the occupants. Controlling lighting to minimize use. Showing an example here of luminaire level lighting controls, but you could also do distributed controls in the buildings. But you want to make sure lighting's only on when necessary, when needed by the occupants, and that it has the ability to dim and control so that occupants have the ability to fine tune the conditions to what's comfortable for them. So making sure also that these controls are going to provide kind of fail-safe operation. Someone can't leave the lights on by accident. The light's not going to stay on 24/7 for some reason. And then also making these as simple as possible. The more sensors you have in the space, the more controls you have, the greater the maintenance load is going to be on the building, and the more likely it is that over time you're going to lose the operational efficiency of that system. So kind of looking at the luminaire lighting level controls, you've got some built-in capability there for space modularity, but again, you've got more sensors, more things that can break down over time and result in long-term loss of efficiency. So there's a bit of a trade-off there. Making sure you're aware of those in your design process is a key element to efficient design. When looking at equipment itself, equipment loads are becoming a larger and larger proportion of buildings, particularly as we get better at designing envelopes and we get better at high efficiency equipment and high efficiency lighting. Now our plug loads are starting to become a larger component of our buildings. And so making sure we're selecting Energy Star compliant equipment that has built-in sleep functions or low power functions where they'll automatically go to those over time when they're not in use is going to do a lot to help improve the performance of the building overall. It'll reduce cooling loads in the building to offset the heat generated by that equipment. Some other control strategies include advanced power strips. Those are coming with the newer versions of the 2021 IECC, have been in ASHRAE since the last code cycle, and controlled outlets as well, where now you've got some ability to turn off non-essential loads when occupants aren't in the space through an automated detection. So you're not relying on people to do optimization strategies. You got a little more automation, a little more ability to make these fail safe. Now let's see if I can relaunch the poll here. All right, so our poll questions now. Which means of heat transfer does the human body feel the most? Conduction, radiation, convection, or evaporation? And how can lighting efficiency be improved in building designs? Using high efficacy designs like LEDs, designing lighting intensity for the space use, and support interior lighting with diffused day lighting, or all of the above. And then we've got a couple of questions that have come in. We've got, does the night light require control sensors, or is it considered emergency lighting that can be on all the time? So there is safe passage lighting in building structures that is allowed to be on 24/7, does not need to be controlled. That is separate from emergency lighting, like fire alarm lighting, things like that, or power outage lighting that's kicked on by a generator or battery backup. Those are typically off or part of the normal lighting operation if they're integrated into fixtures. So those would be controlled, but your safe passage lighting that's in a lot of structures, that is allowed to be on 24/7. Linda, has anything come up in the chat we want to discuss while we're letting the poll go here?
Not yet. I'll make a few announcements at the end.
Okay. We'll go ahead and share our poll results then. Looks like most people caught on. Most people are going to feel radiation the most. Even when you're looking at design and spaces, if you've looked at ASHRAE comfort charts for buildings, the temperature that's listed on those charts is called the operative temperature, which is a combination of air temperature and radiant surface temperature. So even in ASHRAE's comfort standards, they account for that radiant heat gain and loss of occupants. So it looks like most people caught on to that. And then for lighting efficiency, all the above are good ways to improve your lighting design. So good, looks like everyone caught on to those. So I'll turn it back over to Linda to do our key takeaways and wrap up here, and
Great.
I'll take a minute to let my voice rest.
Thank you, Sean. All right. So just a very quick high-level overview, review of what we've talked about, emphasizing again that efficiency should be considered in every step of the design process and construction process as well. So orientation, massing, and layout, the focus there is on passive design strategies that take advantage of the sun while limiting its negative impact. And then with envelope and fenestration, it's all about limiting the heat gain or loss through continuous insulation and air barriers, and paying close attention to those points where you might have thermal bridging. For heating, air conditioning, and ventilation, so selecting efficient equipment is just the start. Sean talked a lot about making sure that the HVAC equipment is sized right, using the controls to optimize for efficiency. And then finally, lighting efficiency comes down to placing LED lighting, so the most efficient lighting possible, only where needed, and using controls to minimize unnecessary use. And then just a quick reminder that the decisions you make in one aspect will influence the other aspects, and design should be an iterative process. So there was a question about the recording. We are definitely going to make the recording available to all of you. If you came in a little bit late, we'll be emailing you a certificate for AIA continuing education credits. And you'll need to fill out a little form that has your AIA membership number on it, and then we can submit that to AIA, and you'll be able to get continuing education credits for that. We'll also send you the recording of the webinar at that time. I also put the link to our website, and I'll also put quickly the link to the upcoming webinars. If you'd like to sign up for the next 2 webinars in our series, we have one on net zero energy coming up, and renewables coming up in April, and then one on passive design coming up in May. So I'll quickly put those in the chat for you. And if you need to go, thank you so much for coming. And if you'd like to stay and ask questions, we're happy to stay on for just a few minutes and answer any questions you might have. Thank you very much for coming.
I did see a comment in the chat about someone has retrofitted LED light kits and old fluorescent fixtures, and that is a great cost-effective option to upgrade existing buildings with LED lighting. But we do note that particularly for new building designs, you can get slightly higher efficacy out of a LED fixture where the reflectors and things in that fixture are specifically designed to focus light down out of that fixture. So you get slightly better performance, slightly higher efficacy, slightly lower installed wattage from a fixture than you would from a retrofit option. But retrofits are a great option. We do like to see those going into existing buildings. Have a request to go back one slide. Go back a slide. Don't see any other questions have come into the chat. No more into the Q&A pane. So in our last minute here, I'd like to thank everyone for joining us today. Again, if you have any questions, please feel free to reach out to us at the contact information here. Energy code at illinois.edu or that 1-800 number is a help desk number. We can give you a quick answer for questions there. Thank you all for joining us today. Hope you have a wonderful afternoon.
Thank you, everyone.